Welcome to the GCSE Statistics Higher Session 4. This session is focused on probability and consists of 4 subsections: two-way tables, probability and odds, tree diagrams, and Venn diagrams. Two-way tables. These questions can be asked in 2 ways. First, they can give you a completed two-way table from which you're going to be asked to calculate probabilities. Or they will give you in the exam a partially completed two-way table. You need to make sure that the final row and column numbers are always row and column totals. Start always with the row or column with only one gap. As you fill in the table, continue in this way. Once your table is complete, or if you've been presented with a completed two-way table, you will then be asked to calculate probabilities using the information in the table. The key part here is to be able to identify what the population is, because this will affect what the denominator is, what you are dividing by. Let's take a look at an example. Example number 1. A farmer wants to find out if a vaccine can stop his sheep getting foot rot. He uses a sample of 100 sheep that do not have foot rot. He vaccinates 60 of these sheep. The two-way table below shows the results. We can see here that we've got a completed two-way table. Each one's in the column here, 10 plus 20 adds up to 30. Same here, 50 plus 20 makes 70. And then each of the rows, our total here is 60, 10 plus 50, 60. Column here adds up to 100, row here adds up to 100. In the next part, we're told that he chooses one of the 100 sheep at random. We know this is therefore to do with probability. And asked to write down the probability that the sheep does not have foot rot. So the probability it does not have foot rot. We look here and we say how many sheep do not have foot rot? 70 out of our total 100. In part B, write down the probability that the sheep had been vaccinated and has foot rot. So vaccinated and had foot rot, we're now looking here with foot rot and vaccinated. Here, out of our total 100. We're then asked, did the vaccine help to stop foot rot? We must give a reason for our answer. Did the vaccine help? Well, let's have a look. Of those sheep vaccinated, 60 of them, 50 of them are without foot rot. So with the vaccine, 50 out of 60 are fine. When we look here at the sheep that were not vaccinated, 40 sheep were not vaccinated and 20 after the period of time did not have foot rot. So that's 20 out of 40. We can see here that the percentage here is higher. We can see here that the ones without foot rot is only equal to a half. Whereas here, the proportion without foot rot is significantly higher. We can just pop this in the same denominator, 6 and 3. So, did the vaccine help? Yes. Why? Because a larger proportion, we can see here, 5 out of 6 of those vaccines or vaccinated did not get foot rot, compared to only a half of those sheep that were not vaccinated. So there's a larger proportion of those vaccinated did not get foot rot. The farmer did not give the vaccine to all of the 100 sheep. Explain why. If the farmer had given all the sheep the vaccine, he would have not been able to tell whether the vaccine was working or not. So, why? Because he needed to compare between vaccinated and non-vaccinated sheep so that he could work out if the vaccine was working. Why? So we're thinking here he did not give all of them because he had a control group, with another way of saying this. You'll be familiar with this from science, to be able to make a comparison as whether the vaccine worked or not. Example number 2. A farmer has 2 farms. On one farm he has battery hens. On the other he has the same number of free-range hens. One Saturday, the sizes of eggs collected from the 2 farms were as follows. Here we must complete. We only have the totals to complete by adding up our columns. So here we have 200, 125 plus 75. Here 420, 230, adding our rows up, 440, 410, and together 850, which you can get from adding these, or these 3 numbers up here. We're then asked to write down the probability that the egg chosen when they're sampling and an egg from those collected on the Saturday is chosen at random. We're then asked to calculate the probability that the egg chosen is large. How many large eggs are there? 200 out of the total number of eggs, 850. We're then asked to write down the probability that the egg chosen is free range and medium. So free range and medium. Free range is here, medium is here. Here, here. This is the number we're interested in. So there's 210 eggs that are medium and free range divided by the total 850. We're then asked to compare and contrast the numbers of different sizes of eggs laid by the free-range hens and the battery hens on these farms. 2 marks are available for this question. We must make 2 comments. So, having a look here, let's look at the large eggs. Free-range hens lay more large eggs. So, free-range lay more large eggs. Look at the medium, exactly the same numbers. So, free-range and battery, the other type of hens, same number of medium eggs. Sorry, that's meant to say same number of medium eggs. 2 comments. Then looking at the small, battery hens make more. There's more small eggs from battery hens. So the 3rd comment, battery, more small eggs. And then if we look at the total, the overall eggs, we can see that the free-range hens are producing more eggs. So overall, more eggs, free range. So any of those 4 comments to get the 2 marks available in this question. Probability and odds. Odds are this is a way of expressing probability. Odds given as a ratio between the estimated number of failures and the estimated number of successful outcomes. So this probability will be expressed as a ratio. If the ratio is against an event happening, the order will be failures to successes. If it's the odds for or on an event happening, the ratio will be in the reverse, successes to failures. So against something not happening, failures first, then successes. Something on or for happening, successes first, then failures. So we have a look at this in the context of example number 3. John and Matt are playing tennis. The odds against John winning a game are 2 to 1. So this is the odds against. So we have failure, success, 2 to 1. So this ratio is not about Matt and John, in the same way that our ratios that we know from GCSE maths are, this is the ratio against John, focusing on John, of winning. So the failure, 2, successes, 1. So when asked what is the probability that John will win the next game, successes, 1 out of 3, the total. So this is equal to the probability of John winning. Okay, think about it in the another way round now. What are the odds against Matt winning? So exactly the same setup as here, the odds against, but instead of John, this time it's going to be Matt. So we're going against winning, so we need the failures to the successes. If the probability of John winning is 1 over 3, the probability of Matt winning must be 2 over 3. So success 2, failure 1. So effectively what's happened here to our ratio is it's just flipped, it's reversed. We're then told that John and Matt play 6 games and asked to work out how many games John can be expected to win. So focusing in on the probability of John here to be 1/3, and he plays 6 games. So we would expect John to win 1/3 of the 6 games. 1/3 of the 6 games are 2. So 2 of the 6 games John should win. Tree diagrams. You need to be able to complete a tree diagram by adding probabilities to the tree diagram. Probabilities can be expressed normally as fractions or decimals, and these will be given to you in the context of the question. They must add up to 1. So if we look here at this tree diagram, the probabilities here on this branch must add up to 1. On this branch, adding up to 1, and same here, adding up to 1. So if the probability, for example, of picking a red ball was 0.4, the probability of picking a blue ball must be 0.6 because they need to add up to 1. If this was a fair coin, the probability of getting a heads is always a half, 0.5, and same for tails, here and here. Now, once the table, the tree diagram is complete, you will then need to be able to calculate probabilities from this tree diagram. If, for example, you were asked to find the probability of getting red followed by tails, red ball, then tails, we would travel through the tree diagram here and then down. And to be able to travel through the tree diagram, we must multiply. We see here multiplying along the branches, So this would equal to 0.4 multiplied by 0.5, which is 0.2. If, for example, we were asked to find the probability of getting tails with any colour ball, tails with any colour ball. Well, it can happen the way we've just said, but it can also happen by getting a blue ball first, then a tails. So there's actually 2 ways we can get a tail. Here, which is equal to 0.2, and here, which is equal to 0.3. So the probability of getting tails, irrespective of whether it's a red or a blue ball, we add the 2 probabilities. That's this point here that we add when we go between the branches. So here we have 0.5. Now you must also be able to understand conditional probability in the context of tree diagrams. Conditional probability is a probability of some event happening given the occurrence of some other event. And there's actually a formula that you can learn to help you. The probability of A, look at the notation, given B is equal to the probability of A and B, both events happening, divided by the probability of B. So, in the context of this example here, we could say, what's the probability of picking a red ball given its tails? So, what is the probability of picking a red ball given that it is tails? So, the denominator must be this given part. So, given the probability of tails, we see here, we know that to be 0.5. So then the probability of red and tails is here at 0.2. So we will divide these two probabilities to find the probability of red, in this case, given tails. And this is known as conditional probability, where one event has happened. And when we're trying to find the probability, given that that's happened, what's the probability of finding another particular variable or event happening? Example number 4. Reading through the information provided in this example helps us complete our tree diagram. To start with, we're told that in a screening test, a saliva sample is taken and tested for bacteria. The result of a screening test can be either positive, this one here, or negative. The probability of a person showing a positive result is 0.1. We're then asked to calculate the probability the person chosen at random will show a negative. And we know here that in the branches, these two must add up to 1. So the answer to part A is 1 subtract 0.1, which is 0.9. Again, we can put that on the tree diagram. You can express it as a fraction, 9/10, or as a percentage, 90%. We're then provided with further information to help us complete this part of the tree diagram. The probability that a person who gave a positive result to the screening test goes on to get tooth decay within the 18 months of the screening test was found to be 0.2 here. We're told the probability that a person gain a negative down here to the screening test does not go on to get tooth decay, D9 minus, is 0.9. So these two pieces of information are given to us in the question. We then need to complete this because we know that these branches must add up to 1. So here we have 1. Now, often we're asked to complete the last section here with the different probabilities. This will help us answer further questions. So here, T plus, T negative, multiplying along, we have 0.08. Here, multiplying 0.9 with 0.1, 0.09. And lastly here, T negative multiplied by D negative is 0.81. Just check 1, 2, 3, 4 should add up to 1. If they don't add up to 1, you've made a mistake. We're then asked, given that a person has tooth decay, so we're asking the probability, given tooth decay, what is the probability that the person gave a positive result in the screening test within the last 3 months? This is part C, and this is what the question is asking of you. What's the probability, T plus, given the person got tooth decay, D plus? So here we can use our formula. We're looking at the probability of them both happening dividing by the probability of tooth decay. So, looking here on our diagram, the probability of T positive here and T plus here. So we have 0.02 divided by the probability of D positive. This one and this one, here and here, here and here. So we must add these up, 0.02 add 0.09 gives us 2/11. If you want to put that on your calculator and give the answer as a decimal, that's also acceptable, 0.18 with some rounding. We're then asked, what can you infer, tell, interpret from this result about the usefulness of the screening test? So the screening test is meant to help us identify the people with tooth decay. We can see here that this test does not appear to be a good predictor of tooth decay. We can see here that out of 11 that got tooth decay, only 2 were predicted. So this test does not appear to be a good predictor of tooth decay. Why? Justify your answer. Because out of every 11 that got tooth decay, this is given that they had tooth decay. Here, tooth decay. Only 2 were predicted to get it. So for those 2 marks, saying no, not a good predictor, and then justifying why. Venn diagrams. Venn diagrams are a really important part of probability and often used to display the information. If possible, you need to start with the middle of the Venn diagram and work outwards. We will see that that's not always possible, but this is a good strategy to bear in mind when answering these questions. You need to be careful of double counting. Check that the totals add up. Really, really important. Let's have a look at example number 5. Here we have 2 categories, radio and television, 2 circles overlapping inside a box. This is a Venn diagram with 2 categories. Here, where I have shaded blue, is radio only. Here, where I have shaded green, is television only. Here, where I have shaded yellow, is radio and television. And everything around the outside here is no television, no radio. So let's take a look now at the numbers. We have here already that the radio is 12. We're told in the question that a health trust does a survey to see how many hospital beds have access to radio and or television. It finds that 21% have access to televisions only. So this part here, the green, is the televisions only, 21%. 12% have access to radios only. That's the category that was already labelled here in the Venn diagram. We're then told that 2% have access to neither. They're the people here outside the hospital beds with no television or no radio. Now remember, this is percentages, so everything must add up to 100. We add our 12, our 21, and our 2, and we get 35%. Therefore, the remaining set percentage here in the middle must be 65. 65% have access to radio and television. It's now time for you to complete some questions. Press pause on the video and complete the question booklet. Once you've done as many questions as you possibly can, come back to the video, press play, and we will go through the questions together. Question number 1. There are 30 people eating in a restaurant. Each person chooses a first course of fish, meat, or vegetarian, and a second course of cake, ice cream, or cheese. The numbers of people eating each combinations at first and second course are given in the table here. One of the 30 people is chosen at random. Write down the probability that this person eats fish for their first course and cake for their second. Fish and cake here. 4 out of the total 30. Write down the probability that this person eats ice cream for their second, given their first course was vegetarian. So only look here at the vegetarian. So we know that they've definitely had the vegetarian first course. So now we are only looking at 7 people. So it's out of 7 because given their first course was vegetarian. How many had ice cream? 3. So really important here, we can see that we're looking just at this row, therefore we have 7 as our denominator. We're then told that John says that people are equally likely to have fish, meat, or vegetarian for their first course. Does the data given support this idea? Well, let's take a look at the totals. How many people had fish? 4 plus 4 plus 3. That's 11. Meat, 12. Vegetarian, 7. Doesn't matter what they had for their second course, but John is saying that people are equally likely to have fish, meat, or vegetarian. Does the data given support this idea? No, completely not. If they were equally likely, we'd have the same number. So no, because there are different number of people having each one of these choices. And especially here, you can see the vegetarian's much lower. So there's not an equally likely chance for them to be having meat, fish, or vegetarian. Question number 2. A holiday in which people can visit 2 cities is called a two-centre holiday. A travel company offers 4 two-centre holidays. The two-way table here shows the number of these holidays booked in 2010. First, complete the table. So we have 4 choices here: Venice and Geneva, Venice and Paris, Rome and Geneva, Rome and Paris. How many people went to Venice? Adding these 2 values up, 56. Rome, 38. Geneva, 50. Paris, going across the row, adding up, 44. Total, adding these up or adding these up, both ways, 94. Which of the two-centre holidays did most people choose? So we're looking for the most popular, the highest number here. So the answer here to part B, what did most people choose? Paris and Venice. Y, justify your answer. Highest number, highest frequency, some reference to 32. A person taking one of these holidays is chosen at random. It's going to be a probability question. C. What is the probability that this person visited Rome and Geneva? So not Rome or Geneva, they've got to have gone to Rome and Geneva. So Rome and Geneva, we're looking here, 26 people, Geneva and Rome. So this is the probability we're looking for, 26 out of the total number, 94. Part D here, we have a conditional probability question. Given that this person visited Venice. If they visited Venice, we are now only interested in this. So, given they chose Venice, visited Venice. They visited Venice, therefore our probability is out of 56. We know that we're selecting from random from those people that were in Venice, 56 of them. How many of them also visited Paris? We have here our value for Paris, so 32 out of 56. This part here is really important that you're correctly selecting the total population, which is not 94, but the total for Venice, because the question says, given the person went to Venice. Question number 3. Helen and Jan are playing badminton. Helen's odds for winning a game are 3-2. For winning a game, success to failure, because it's 4, 3-2. Write down the odds against Helen winning the next game. Against is failure to successes. So we must flip our ratio 2 to 3. Write down the probability that Jan will win the next game. Well, what's the probability of Helen winning? Probability of Helen, looking here for our successes, success to failure, again here, success, 3 out of 5, the total. Therefore, the probability of Jan winning must be 2/5, because these must add up to 1. So the probability of Jan is found from using the probability of Helen. Helen and Jan play 20 games of badminton. Work out the number of games that Jan can be expected to win. So the probability of Jan winning, we can see here, is 2/5. So we want to know 2/5 of 20 games. We can do this by multiplying 40/5, which is the same as 8. We can do it also by 20 divided by 5 equals 4, times by 2 equals 8, because we're interested in 2 parts. So here we're doing 2/5, the probability of times 20. Question number 4. You need to read through all of the probabilities given and match them to the appropriate place on the tree diagram. Let's do this step by step. Joan catches a bus, cycles or drives to work. The probability that Joan catches a bus is 0.4. The probability that she cycles to work is 0.5. The probability that she drives to work is 0.1. These 3 probabilities add up to 1. When Joan catches a bus, this one, the probability of her being late is 0.2. Therefore, the probability of her not being late, they must add up to 1, is 0.8. When she cycles to work, the probability of her being late is 0.3. Probability of her not being late must be 0.7. And lastly here, when she drives to work, the probability of being late is 0.1. Therefore, the probability of not being late is 0.9. A day is chosen at random. Find the probability that Joan is late for work. How can she be late for work? She can take the bus and then be late. She can cycle and then be late. She can drive and then be late. There are 3 different ways of her being late. We must calculate the probability of each one by multiplying across the branches. Once we have the 3 probabilities, we must add them up to find the total probability of being late, 0.24. We're then told that Joan was late on Monday. She was late. Work out the probability that she caught the bus. This is conditional probability. We're looking for the probability she got the bus given she was late, which is equal to the probability of bus and late, all divided by the probability of late. We've just worked out the probability of being late, 0.24, and then we're asked to find the probability of bus and late, bus and late, bus and late is this one. So here we have 0.08. Again, we can leave this as a fraction, 1/3, or as a decimal, 0.3 reoccurring. So this is given she was late, work out the probability she caught the bus. In the same question, given she was late, work out the probability that she did not catch the bus. The probability she did not catch the bus will be 1, take away the probability she did take the bus. 1 take away 1/3 is equal to 2/3, or as a decimal, 0.6 reoccurring. This here comes from the probability of something not happening is equal to 1 take away the probability it does happen. Question number 5. Michael throws a stone at a target. He then throws a second stone at a target. The probability he hits his target on his first throw is 1/5. Look here, first throw, hit, 1/5. These 2 probabilities must add up to 1. Therefore, the probability of miss is 4/5. We're then told if he hits the target this way on his first throw, the probability he will hit his target on the second throw is 1/3. Therefore, these 2 must add up, the branches here must add up to 1, 2/3. We then have, if he misses the target on his first throw, the probability he will hit his target on his second throw is 1/4. This is different to the probabilities here. If he misses his target on his first throw, the probability he will hit his target on his second is 1/4, not 1/3. Therefore, the miss will be 3/4. Must add up to 1. Now that we have the tree diagram completed, we're then asked to calculate some probabilities. Our first probability for A is to calculate the probability that he hits the target on both throws. So using a highlighter, starting here, hit, hit. This is hit on both throws. When we move through the tree diagram, we must multiply across our branches. There is only one way that he can hit and hit. We calculate the probability, 1 over 15, multiplying through the tree diagram. In part B, we're asked to calculate the probability that he hits the target only once in the 2 throws. It doesn't matter if he hits the target on his first or second throw, but he must hit only once. Take another pen. If he hits once on his first throw, only once, he must then miss. However, this can happen another way. He could miss his first throw, but then hit his second. So in this case, we have 2 ways that he can hit the target only once. We must calculate the probability of each of these 2 outcomes and then add them together. So our first probability, we multiply through the tree diagram. We have here 1 over 5 multiplied by 2 over 3, which gives us 1 times 2, 2, and 3 times 5, 15. The second way, by missing the first and hitting the second, has another probability, 4 over 5, multiplied by 1 over 4, 4 over 20. We then need to add these 2 up. Adding these 2 up, we have a final answer of 1/3. The probability of hitting at only once is equal to 1 over 3. Question number 6. Here we have that a travel agent organises several different tours to Germany, France and Switzerland. Each tour goes to 1, 2 or 3 of these countries. We're then provided with a list of information about the number of people that went on the different tours. We need to start at the bottom, looking at here the 50 people who went on all 3 tours. Went to all 3 countries. That's the people here in the middle, 50. Then working our way up, looking at our next category, that's 75 people went on a tour to Germany and Switzerland. Taking the colour here, you can see that Germany and Switzerland, these 2, share this space. So everyone in here needs to add up to 75. We do not write 75 here. We already have 50 people in the yellow category, Germany and Switzerland. So our remaining 25 goes here because 75 people went on tour to Germany and Switzerland. Looking now to the 84 people that went on tour to France and Germany. Taking another colour, we will look here on the green. This section is for France and Germany, and it needs to include 84 people. 84 people to Germany and France. We have 50 already here. Therefore, we need 34 here to add up to 84. Similarly, between Switzerland and France, taking another colour, we are looking at this section here. Between Switzerland and France. Switzerland and France is 74. We have 50 already in this category, so we must add 24 to make 74. We are then told that 122 people went on tour to Switzerland. If we look here at Switzerland, everyone in the Switzerland circle must add up to 122. Let's take a look at how many people we've got in here already. We have 50, 25, and 24. Adding these up, we have 5, 6, 7, 8, 9. 99 people. 122 altogether. Therefore, in this space here, we are missing 23. These are the people that only went to Switzerland. Okay, now moving on to our next category for France. Everyone who went to France needs to be inside this circle. How many? 1, 3, 1. How many people do we have already in the France category? 34, 50, and 24. 108. 108 already, and we have the fact that 131 went to France together. Therefore, we also have 23 people who only went to France. Lastly, we are looking here at our last category. This category is for Germany. This here is the red circle that everyone inside the red circle went to Germany, and there is 130. 130 people, but we already have 34 plus 50 plus 25. Adding those up, we have 109. We have 130, therefore 21 people just went to Germany. Now we can see here our 0 means that everyone needs to be included in this Venn diagram for Germany, France and Switzerland. Before moving on, take your calculator and quickly check that each one of these numbers, when you add them up, you get to the number in the question, which is 200. You must add up these numbers, check that they add up to 200 before you move on. Question number 7. There are 100 students at a music school. Here we have 12 of the students play violin, piano and violin only. Piano and violin only. That means in this section here, directly goes 12. 7 of these students play violin and oboe only here. They do not play piano as well. 30 of them play piano and oboe only. 84 of the students in total play piano. So we have to add these up. 30 plus 32 plus 12 will give us 74. So 84 play piano. We have another 10 students here. Same here, 57 of the students in total play the violin. So 32 plus 12 plus 7 gives us 51. So if 57 play the violin in total, here is another 6. We're told that there are 100 students. So to be able to find the missing number in here, we must add everything up and subtract from 100. 3 only play oboe. Of the 100 students, one of the 100 students is picked at random. write down the probability that this student plays piano and oboe. Not piano and oboe only, piano and oboe. Piano, oboe. This section in here. So for part B, probability of piano and oboe is equal to 62, the total, divided by 100. 100 students altogether. We're then told, given the student plays piano. Given the student plays piano. Therefore, the student is in this circle. The population is the total of here. So, given that they play piano, therefore our probability is going to be out of 84. Find the probability that this student also plays the violin. Where are the people that also play the violin? They're these people here. 12 plus 32. 12 plus 32. 44 over 84. Is your answer to part C. We've now come to the end of session 4. Please revise the list of topics shown here on the screen and replay the video for any section that you would like to study again.